Hello friends, today I will discuss about on-load tap changer or OLTC of transformer and how by changing tap position LV side voltage can be regulated. In this diagram, a single line diagram has been shown how the power is transmitted from generating end station to distribution end substation. From generator, the voltage is generated at a voltage of 11 kV, and to transmit to load end, it is further step up by means of step up transformer, that is 11 kV by 132 kV power transformer. So from substation A end to substation B end, the power is transmitted through 132 kV or any extra high voltage transmission line in order to minimize the losses of the transmission line. Again, at substation B end, the power is stepped down by means of step down transformer, that is 132 by 33 kV transformer at substation B end. Then different 33 kV feeders are taken to the distributed substation, that is substation and C. In the distribution end substation, again the voltage is stepped down by means of 33 by 11 kV transformer, and different 11 kV feeders are taken to the consumer end to supply the either for direct for 11 kV consumer or domestic supplies to supply the pole mounted transformer. So this is how the generating power is transmitted from generating substation to 11 kV distribution feeder and again to the consumer end. Now why the OLTC, that is on load tap changer, is required? So there are two types of tap changer. One is on load tap changer and another is off load tap changer. In case of on load tap changer, there is no requirement of shutdown of the transformer. The tap changer, that is tap position, can be changed remotely in online mode. But in case of offload tap changer, we have to take shutdown of the transformer and then the tap position can be changed. Normally in case of distribution substation, there exists offload tap changer, and in case of grid substation there exists on-load tap changer, that is 10 MB and higher rating of the transformer. So we know that Vt is equal to Vs minus I into Z, where Z is the line impedance and I is the load current, and Vs is the source end voltage and Vt is the terminal end voltage. So if the load current increases, then there will be more drop of the line, and therefore the terminal end voltage will decrease. So during heavily loaded condition, for example, if 11 kV feeder is heavily loaded, then 11 kV terminal end voltage at pole mounted substation will decrease, and again at substation C end 33 kV voltage will be decreases. So in case of distribution substation, there is no provision for on load tap changer, so tap must be increases from the substation B end or grid substation end. So by means of tap changing in online mode, that 33 kV voltage can be increased to up to 35 kV, so that at distribution end the 33 kV voltage should be retained. This is how the tap changing helps to regain the voltage profile at distribution substation. Normally tap winding is provided in the HV side winding in order to handle lesser amount of current. In the tap winding, there exists make before break contact, so that during changing of the tap position, arc does not occur. So in this diagram, a 132 by 33 kV star HV side is star connected and LV side is delta connected transformer winding has been shown. In the HV side, the tap winding is provided. The 1.2 number is the selector switch position, and there exists 3 to 19 number tap position. that is if the 1.2 number selector switch is connected at the 3 number, then number 1 tap position will be selected, and if the 1.2 or selector switch is connected at 11 position, then a nominal tap position will be selected, and if the selector switch is connected to the 19 number, then the tap position 17 will be selected. So there are 17 number of tap position. By means of changing this tap position, the voltage can be regulated in the LV side. By means of the transformer induced law, that is V1 by N1 is equal to V2 by N2, where V1 is the induced voltage in the HV side winding and V2 is the induced voltage in the LV side winding. And N1 is the number of turn in the HV side winding, and N2 is the number of turn in the LV side winding. That is, volts per turn in the each side shall be same. So in this nameplate, the tap on HV for HV variation has been shown. Here the 33 kV or LV side voltage is taken as a constant, and the tap position is changed from 1 to 17 number, and by connecting the lead connection from 1.2 to 19. If 1.2 that is lead connection is taken to the 19 number, then maximum tap position or maximum winding is utilized for HV side winding, where the maximum voltage in the HV side would be 145.2 kV, and line current for HV side shall be 198.8 ampere. When the lead connection is taken at position number 11 in the tap winding, then nominal tap will be selected, that is 9 number tap position will be selected, and therefore the line voltage is nominal line voltage, which is 132 kV, and line current is 218.7 ampere. Again, by increasing the tap position from 10, 11, 12, the selector position, that is 1.2, shall be changed from 11 to 10 to 9 to 8, and so on. Again, for minimum tap position, that is at 17 number tap, the lead connection shall be at number 3 position. So in this lead connection or tap position 17, the minimum winding tap winding will be selected, and here the line voltage for HV side shall be 118.8 kV and line current shall be 243.0 ampere. From the above table, we can calculate the N1 by N2 in terms of ratio of the V1 by V2. So at tap number 9 or at nominal tap, the N1 by N2 is equal to V1 by V2, which is 132 by 33, which is equal to exactly 4. At tap position 10, that is V1 by V2 is equal to N1 by N2 equal to 130.35 kV by 33 kV, which is equal to 3.95. At tap position 8, V1 by V2 is equal to N1 by N2 equal to 133.65 by 33, which is equal to 4.05. And at tap position 7, N1 by N2 equal to 4.1. So the turns ratio at different tap has been tabulated in this figure. So at tap position 1, that is at maximum tap position, the ratio of the primary winding to the secondary or LV side winding is maximum, since at tap position 1 the maximum tap winding is selected, that is N1 by N2 is equal to 4.4. At tap position 2, N1 by N2 is equal to 4.35, and thereby it is decreasing at up to tap position 17 by means of 0.05. So at tap position 9 it is 4, and at tap position 7 it is 3.60. So at tap position 17, that is at minimum tap position, it is the tap winding is minimum is selected, and the turn ratio is 3.60. Now how the LV side voltage can be regulated by means of changing the tap position. Since V1 by V2 is equal to N1 by N2, so the V2 is equal to N2 by N1 into V1, or V1 by turns ratio. So at no load, at a nominal tap position, that is at tap position 9, the V2 is 33 kV, and during loaded condition the V2 needs to improve, so that at distribution end substation the HV side voltage can get up to 33 kV. Since there is more load, there will be drop in the transmission line, and so the terminal voltage at distribution end substation drop from 33 kV to almost 31 or 32 kV. So by changing the tap position from 9 to 10, that is the turn ratio is reduced. So since N1 by N2 ratio is reduced, so the V2 is equal to V1 by N1 by N2 will be increased. So at tap position 10, the V2 that is the LV side voltage shall be equal to 132 by 3.95 is equal to 33.418 kV. Again, by changing the tap from 9 to 11, the V2 shall be 132 by 3.90 is equal to 33.846. So you can see that by changing the tap position from nominal to 10 and 11, the LV side voltage can be increased. So in this table, how that LV side voltage can be regulated for different tap position has been shown here. At tap position 1, that is since it is the maximum winding, tap winding is selected for HV side winding, the N1 by N2 ratio is maximum, that is 4.4. So at tap position 1, the LV side voltage would be minimum, that is 30 kV. Again, by increasing the tap number, the LV side voltage shall be increased by 30.34 kV, 345 kV at tap position 2. At tap position 3, the voltage shall be 30.698 kV, and so on. At tap position 9, at nominal tap, the voltage shall be 33 kV, and at tap position 10, the voltage shall be 33.418 kV, and by so on. At tap position 7, that is the minimum of the HV side winding is selected, so the maximum voltage at LV side can be selected. So at tap position 17, the V2 or LV side voltage shall be 36.667 kV. So friends, if you like my video, then do subscribe my channel, and thank you for watching my video.